Welcome to NET410. This is a deep dive on DNS in the hybrid cloud, for those of you who haven't read the obvious. If you're not your company's DNS geek, not sure if you'll love this, but this is a deep dive in DNS. So I was my company's and am one of my company's DNS geeks. I've been one of the Amazon DNS geeks for some years, and a couple of years ago I was presented with a new challenge, which was to work with the team to build what turned out to be Route 53 Resolver. Spent quite a lot of time on it, and I'll explain a fair bit about it today. So just briefly what we will do is I'm going to go through Route 53 Resolver and what that is exactly, briefly, and then talk a little bit about hybrid clouds and the challenges that come up there. And then we'll talk about the new features we launched last year, which were inbound endpoints and outbound endpoints and rules. And then a kind of specific use case with Active Directory, and then a topic that comes up quite a lot with customers, which is managing DNS across a large number of VPCs. So Route 53 Resolver. In some sense, Route 53 Resolver has existed for as long as EC2 has. There's always been a DNS resolver in the VPC. And even before the VPC. But it didn't really have a name. And then we started adding new features to it and realized we have to give this thing a name. And as it's very tightly coupled with Route 53 and Private DNS, we decided to call it Route 53 Resolver. So this is the VPC resolver that you have known for many years potentially. That's just what we're calling it now. It's also sometimes called Amazon Provided DNS, the .2 resolver, the +2 resolver, various different names it's had. And then in Q4 last year, we launched Resolver Endpoints and Forwarding Rules, which are the first new features of Route 53 Resolver. So very quickly, just to talk about the resolver itself. In the cloud, we have VPCs. If you're working with high availability or trying to look after high availability, you'll probably have instances in multiple availability zones. And out of the box, each of those will be configured to use Amazon Provided DNS, which is the typical address is the VPC CIDR address +2. And what that actually is really somewhat like a gateway endpoint. If you've ever used gateway endpoints with S3, it's not really exactly a host on the network. It's really a gateway that gets you to a shared resolver service that's multi-tenant that everybody uses. And the shared resolver service is built out individually in each availability zone for isolation. And what the resolver is actually doing is forwarding queries to multiple different targets potentially. So if we zoom in a little bit on the left half of that picture, you have an instance calling this VPC CIDR +2 address. It also has this 169 address, and that's forwarding to the resolver for you. And the 169 address, I guess, is kind of a clue. This isn't exactly a host on the network in the usual way. Some people have a picture, which is not an unreasonable mental model, to say, oh, they probably stand up instances running bind. And it kind of looks like that. But in practice, it looks a little bit more like this. So on the hardware where your instance resides, in the hypervisor, is where the .2 really lives. And so although if you think about the VPC CIDR address +2, you might imagine that's a particular subnet. It's not. It lives on the hardware with your instance. And that's why it also has that local address as well. And so one other thing to know about this is that there is a packet limit, which is in the documentation, that one instance can only send 1,024 packets per second to that .2 address. And finally, there is a layer of caching that exists at the VPC CIDR on the box. So if you make 2 queries in quick succession for something with a non-zero TTL, the second one will probably come back to you in microseconds because it hasn't even left the box. So there's a layer of caching there that kind of improves performance and generally helps out. Initially, there wasn't on the Nitro instances, but that is there now. So all of the instance types have that. And just so we're clear, I'm kind of giving you some internal details here. It's not a guarantee that that will be true or that will be how we'll do it forever, but it is the way we do it right now. And it's kind of useful, I think, when you're thinking about how to plan things to have a little bit of extra insight like that. So looking at the other half of the picture, we have this multi-tenant resolver service, and we zoom in on that. So what it's actually doing is classifying queries. So it looks at the query name and what VPC the query came from. And so the first thing it checks is this a private DNS zone? So when you associate a Route 53 private zone to a VPC, the resolver on the left there has that list of associations. That's all it has. But it knows now, okay, this is a private zone. This query is for a private zone. I'll send it to target number 1 there. There are also VPC DNS, a VPC DNS authority, which is for the instance names, the EC2 instance names that are automatically generated are answered by that. And the PTORs, the reverse records, are also answered by that. And finally, if neither of those is a match, it will just send it out to the public DNS authorities as usual. So briefly, how does private DNS work? As I mentioned, a list of private hosted zone associations are given to that resolver so that it can forward to it. If the queue name, the query name, or the queue name in the query matches a given private hosted zone, we forward it to that. It's important to understand the priority here. Private DNS is first in the list. So for the sake of argument, if we were to create a private hosted zone called dot, the root of DNS, that literally will win everything. So you can actually, if you want to, create a blank slate of DNS and add all your own records in and see nothing else. But your VPC instance names go with it, so you'll have to recreate those. So a minor, or just not minor, but a thing that's kind of tangent that I wanted to mention here in case you haven't seen it. As of about 10 days ago, we launched private DNS support for overlapping zones. So previously, if you created a zone called example.com, you couldn't then also create a zone called foo.example.com. And now you can. And this is kind of handy because private hosted zones are associated to a specific account. So if you want 2 different accounts to be able to manage a parent domain and a child domain, you can do that with different accounts now. So the other authority, the second authority in the list, was the VPC DNS. And so there are basically a set of special namespaces which are instances, and they're specific to a region. So I've chosen London for no particularly good reason here. So EUS2.compute.internal is one of those instances are in there, so that will always be forwarded to that authority. The RFC 1918 reverse spaces are also forwarded to that. And then the public namespace for the instances is as well. And so if you ever set up something like an RDS instance or any instance with a public IP, you probably know that it uses an internal IP and a public IP. And in DNS inside the VPC, if you query the public name for it, you'll get back the internal IP. And so this is how this is done, is by forwarding it to that authority that knows the mappings. And if you're ever looking to understand this better, one trick that's handy is you can make a query for the SOA record, and you can see there EUS2.compute.internal. That tells you that this namespace is being answered by the VPC DNS. And there's a similar one for private DNS as well. Okay, so in summary, that is the order in which this happens. You have private DNS first, then VPC DNS, and then public DNS. So very quickly, if we make a query for private.my.vpc, which is a private DNS zone, what will happen is the query will go through the .2, classified at the resolver, and go to Route 53 private DNS. Make a query for an instance name, it will go to the VPC DNS authority. And if we query for S3, which is just a plain public name, it will go to the public DNS authorities. And again, we haven't crossed availability zone at all here. All of those queries are staying inside the availability zone, obviously excepting where we have to go out to a public authority. So, just summarizing the VPC plus 2, it has a lot of really good features. It is super simple. There's basically almost nothing to do to get it working, which was how it was intended. It's very scalable. in that although there's a limit of 1,024 packets per second, that's per instance. So if you have 10 instances and you decide the next day you need 20 or 30 or 40, each of them is going to get 1,024. It's not shared. It's very fault tolerant. The way that architecture works, there's a small cache on every instance. The forwarding is done individually on each instance. All the queries are siloed within an AZ. So there's very good isolation between the availability zones and very good fault tolerance within it. It's also pretty performant. That extra layer of caching is really good. And the fact that we don't cross AZs is good. And it basically doesn't really cost anything. You're obviously paying for the instances, but there's no extra charge on queries or anything like that. So if we talk about hybrid clouds, the picture changes. I imagine this is fairly obvious to you guys. You add a corporate network of some sort or some other network. It probably has a DNS resolver. Almost every network does. And we'll connect it with Direct Connect. So what we now have is IP connectivity between the VPC and the on-premises network. But the problem that we still are left with is, although they can connect to each other if they know the IP address, they can't resolve the names for each other. So if we make a query, or if that server is trying to make a connection, it will use that DNS resolver. And if it's trying to connect to an instance in EC2 or something with a DNS name in EC2, it won't be able to resolve it. So what we would like to do logically is some kind of forwarding. Like let's say we have a bunch of private hosted zones and we have the EC2 instance names. We want those to resolve on premises. So we want it to be able to tell that DNS resolver, just forward the queries into that VPC resolver, right? That was what everyone tried to do, and unfortunately that doesn't work. For the reasons that I explained a minute ago, this .2 address doesn't actually live as a real address in the VPC. It lives on the instance hardware. So you can only call it if you are on instance hardware. So what you would like to be able to do would be that. But that doesn't work. Equally, in the other case, if your instances need to talk to some service on premises, you have the same problem. The DNS for the on-premises is probably managed on that DNS resolver on premises. So you'd like to be able to forward maybe from the VPC resolver back to the DNS on premises. Something like that. But until recently, there was no way to do that. And until this time last year, the pattern that was always given was this one. We did it for a number of years. So you would set up, the customer would set up a couple of instances. Those instances are running on real EC2 hardware, and they can call the +2 resolver. And then you would create forwarding rules on the on-premises DNS resolver to say all those EC2-based names, send them to those DNS forwarders. And then you would configure the DNS forwarders. They'd probably run Unbound or Bind or some kind of DNS software and conditionally forward either to the +2 if it was an EC2 name, or to the on-premises resolver if it was an on-premises hosted DNS name. And then you would, last step, change all the instances or change the DHCP for the VPC to point the name server setting at those forwarders. So a query for a mycompany.com name that's on-premises would do that. And you'll notice that both queries went to the same DNS forwarder there. And that is because of the way the Linux stub resolver works. I'll come back to that. So a query for an instance would go to the VPC DNS via that DNS forwarder. And this was extended further. A lot of people set up a hub and spoke network where they have multiple teams, multiple VPCs, and maybe they're connected with Transit Gateway or peering. And so they all change their DHCP to point at the central DNS forwarders. And so again, a query can go like that. And a query for an S3 name would go like that. So forwarding instances worked pretty well. They weren't perfect, but they enabled a lot of work for people. It largely works. You could pretty much do whatever you wanted in terms of customizing DNS, forwarding it whatever way you wanted. It was, particularly for somebody who was running a lot of VPCs with a lot of services, the cost wasn't that high in terms of instances. You were probably talking a small number of instances. It has a cache as well, although you have to call potentially cross AZ to get to it. So maybe not quite as good as the local cache that you get on an instance. And it's very flexible because you're able to configure the software yourself. You can do logging and RPZ and all kinds of things. We saw people do zone transfer. But there were a couple of rough edges. I mentioned before that all these queries appear to be going through the first DNS forwarder. And what if it fails? Which, every host fails at some point. What happens is, because of the way Linux's DNS resolver, stub resolver works, it will always query the first IP and then query the second one after a relatively lengthy timeout in seconds. I think the default is 2, but you can't really practically set it below 1. So the impact of that one instance failing is actually pretty severe here. So this is the Linux stub resolver config. You can see the timeout of 2 there, and you can see ordered name servers. And that 4.10 is going to get nearly all the queries. And it will only query 3.10 if 4.10 doesn't answer. And you can see that in the man page in resolve.conf. So there were some challenges with forwarding instances. The big one that we heard from customers was not so much the failures as just the weight of building and managing these. And adding your own monitoring, and it was a whole extra setup custom component that most customers didn't really want to own. Those limits were a problem. The 1,024 packets per second limit became a VPC-wide problem because every instance is sending to the one EC2 instance. It has a 1,024 limit, and it becomes a bottleneck. It doesn't deal very well with instance failures because if that one instance fails, as I said, it doesn't work that well. And we've also broken AZ isolation here. We're really relying on the AZ where the first instance lives. So a quick sort of comparison between just using the +2 resolver and forwarding instances. If you could use just the VPC resolver, things were better in the sense that it's fully managed. You had a much more scalable limit for every instance. It was zonal, but it did not have on-premises integration, and that was the key missing thing, at least for most customers. And so forwarding instances, the on-premises integration won out, and that was what a lot of people did. So Route 52 resolver endpoints were built to address this problem. And I'll talk specifically about inbound endpoints first. So what we wanted ideally was for the DNS resolver to just be able to call that VPC +2 address somehow. We can't quite do that, but what we can do is inbound endpoints create ENIs that are reachable. So create real addresses on the network that gateway you to the resolver service. Just a minor thing, when we talk about an endpoint, it consists of multiple ENIs. There's a limit of 10,000 QPS per ENI, and I think you can create up to 8. So there's a fairly high limit on these. So what it looks like is an inbound endpoint drops in with a single API call just like that. And so that allows that DNS resolver on premises to send queries to the resolver. And it really is that simple. There's not really very much more to say. A little bit about best practices on it. So we always recommend having multiple ENIs. This is the same story you hear from every solutions architect, right? Multiple availability zones. Same thing applies here. You want to have ENIs in at least 2 availability zones for high availability. Also, you want to have, I wouldn't recommend setting up all your hosts on premises, your just random hosts, to query those ENIs. It's better to have a caching forwarding resolver on premises sending to them. It gives you better performance because of a cache on premise, and it will give you a better, a forwarding resolver will retry more effectively if one of them is down. It won't tend to forward just to the first one all the time like your hosts will. I would also always specify your IPs. You can let that be kind of, pick them randomly, but keep in mind that you're going to hard code those IP addresses in the resolver on premises in forwarding rules. So you want to specify those. As there are limits on those ENIs, we publish metrics, and we would always recommend people keep an alarm on those. So there's a couple of different scenarios. One is just as things grow, you may want to add extra ENIs, and you want to get an early warning sign before the problem arises. When you're thinking about capacity of these, plan for the failure of one of them. So if you're running them at 6,000 QPS, 60% of the limit, and you have 2 of them, you have a problem. That means if one of them fails, there's too much for the other one to handle. So you should probably, for that load, have 3. Up to you, but that's how I would think about it. Finally, we wouldn't recommend inbound endpoints, for your EC2 instances. It is much better. The VPC plus 2 resolver has a lot of properties with AZ isolation and other things that it is still the best resolver for your EC2 instances. So, a few questions that always come up. Do I need multiple endpoints if I have multiple VPCs? Generally speaking, no. In a single VPC, if you have a lot of private hosted zones, you can associate them all to that one VPC. It makes your on-premises forwarding rules much simpler. Just send them to that one endpoint, and it's cheaper as well. Also, most of the instance names are common across all VPCs and will be answered by any VPC, so it doesn't matter too much. I mentioned before there's a private-public IP relationship, and as long as those VPCs are peered, you'll get the internal IPs for any of the VPCs. So here's an example with a hub and spoke setup. Again, we have an inbound endpoint, and we had 3 private hosted zones, 1 on each of these VPCs, and that DNS resolver on premises needs them. So we just associate them all to the central hub VPC. You can create inbound endpoints in every VPC, but it's not necessary. So any query will just do that. So just a quick comparison with the forwarding instances. By contrast, inbound endpoints, fully managed, have a relatively high limit of 10,000 QPS, which is much higher than the 1,024 you would have got from a forwarding instance. There isn't caching actually on the inbound endpoint, but there is at the resolver behind it. It has a zonal blast radius. They're similar enough on that. It also publishes query metrics out of the box, which is kind of handy compared to having to figure that out for yourself when you're monitoring the instances. So the other half of the problem is solved by outbound endpoints. So I mentioned before that what we would want, we've got some zones on premises that the EC2 instances need to resolve. So we want to be able to make a query for one of those mycompany.com on-premises names. But what happens is the query just goes out to public DNS authorities and probably returns NX domain or a public IP for the same thing or something you didn't want. So what an outbound endpoint does is effectively establish a path for our resolver, the Route 53 resolver, to query your hosts in your VPC or on premises. So we create source ENIs that queries come from. And it's usable by many VPCs. I'll come back to that in a minute. Again, one endpoint is multiple ENIs. And again, the limits are 10,000 QPS per ENI. So when you make an API call, they drop in like that. And so what we've got here now is a path for the resolver to forward out to that DNS resolver. The Route 53 resolver, to forward to the on-premises DNS resolver. But when we make the query, it still goes to the public authorities because we didn't create any rules yet. So all we've said is, here's connectivity. We haven't told the resolver to use it. So resolver rules are the other piece. And this allows you to configure how the Route 53 resolver makes decisions. There's 2 types of rules right now, forward and system. And the system is let the original resolver system answer it. A forward rule is forward it to some resolver of my choosing. So now we create a forward rule in that VPC and associate it, to that VPC. And now when we make that query, it will go through the outbound endpoint to the DNS resolver on premises. So a few questions have come up here. Do I need multiple outbound endpoints for multiple VPCs? Because you're going to want them all to be able to make queries to on-premises. And the answer is no. If you have a hub VPC where you tend to manage your DNS, you can put the outbound endpoint there, create rules that refer to that endpoint, and then associate those rules to many VPCs. Do you need to share the outbound endpoints? No, just the rules. And because the rules refer to the endpoints, they'll effectively use the endpoints implicitly. If the VPCs are in different AWS accounts, you can use Resource Access Manager to share between accounts those rules. And do you need VPC peering or transit gateway here? Logically, it sort of makes sense that, well, in order to make queries to the resolver in the other VPC, I'm going to need connectivity. Actually, you don't. If you look at this picture here, everyone in the spoke VPC1 and spoke VPC2, they're just sending their queries to the resolver via the +2. So when we put the outbound endpoints there, the resolver has connectivity. So first of all, we've created the rule, we've put it on the hub VPC, and that allows that VPC to make queries via the endpoint. And then we associate those same rules to each of the other VPCs, and now they can make those queries. And while it's not uncommon to have transit gateway there or peering there to connect those together, it isn't necessary for a lot of people. So you can just remove that. That's not necessary. So a few best practices when you're dealing with outbound endpoints. Again, multiple ENIs in multiple AZs. You've all heard the drill at this point, I think. I would typically use forwarding quite sparingly. It is a UDP protocol DNS. All it takes is one packet to be lost, and you're going to wait for the DNS resolver to retry. So as a general rule, also considering how critical DNS resolution is, you want to keep your DNS data plane as simple as possible with the fewest number of hops involved. So try to keep things in the local AZ. Try not to use forwarding where you don't need to. Though it is obviously necessary in some situations, and that's totally reasonable. But if you don't need it, would prefer not to use it. Again, maintain fixed IPs. These are the IPs on premises now. Don't change your DNS resolvers on premises. You probably don't do that anyway. If you're used to dealing with DNS, changing the IP addresses of your DNS resolvers is not pleasant. Again, you want CloudWatch alarms ideally, so that if you get a spike in traffic at some point, you'll get an alarm. You won't have to debug things and figure out, oh, it's because we're hitting that limit. You'll get an alarm that tells you you're hitting the limit. And also, as you slowly are growing, you get an early warning sign that says, yeah, we probably need another ANI. So again, a comparison with forwarding instances. Now we have a fully managed solution. It scales quite a lot better. So every instance now gets 1,024 queries per second. And the outbound endpoint, which is only taking the forwarded queries, gets 10,000 queries per ENI. So that scales a lot better than the forwarding instances. Sorry. The other thing is that now that obviously the VPC resolver has on-premises integration, so the thing that it was missing is there now. So a few things about the rules in terms of how they work. What if you create rules that overlap? So you create two rules, one that's example.com and one that's foo.example.com, and then you query bar.foo.example.com. What happens? The most specific matching rule wins. I think a good analogy if you're used to dealing with routing tables, it's always the most specific route wins. It's pretty much the same here. If you have two rules on the same domain, a forward rule, which is definitely created by you, always wins over a system rule. How do these rules interact with private hosted zones and VPC DNS? So obviously there's a bunch of logic that we already have here that's doing classification of queries. And it was very important when we were designing this to say, well, okay, we cannot change that at all because there's so many customers who already rely on it. And it doesn't technically do most specific query if you think about it. If you create a dot on the private DNS, there are more specific names, but they don't win. So we couldn't really change that behavior, so what we came up with was something like that. And so what we do is we apply rules first. And then the rules either decide to forward queries to whatever resolvers you have, or we send it to the original system and it works the way it always did. And this is nicely backward compatible. So let's just suppose, for the sake of argument, we create a forward rule on dot. It's kind of an extreme thing to do, that all queries should go to the on-premises resolvers, but some people need to do that. But it creates this question of, well, did I just break all my private hosted zones? How does that work? So in order to, we know that that's not what people want as a general rule. If you've created a private hosted zone and you have it associated, you presumably want it to work. So what we do is we create these auto-defined system rules. And using that analogy of the routing table, if you create an interface, it always creates a route for you. And this is kind of like that. There are certain indications that we know, similar to you have an interface on that address, that say, yeah, we should have a rule for that. Don't break those. So the auto-defined system rules that we create one for dot, which is basically all queries go to the system if you do nothing else. And we create one for each of those namespaces that I referred to before, which are the VPC DNS. So we don't want the instance names to break when you create a rule on dot. And we create a rule for each /24 in the VPC CIDR. So that's basically saying these are the IP addresses that are actually in use for instances. And we assume by default that you want us to answer them. But you can override that if you need to. And finally, if you have private DNS zones, if you don't want them to work, you should probably remove them. But we create rules for those so that they will win if there is a dot rule. So here's a specific example from a customer. So he wants to forward all public DNS resolution through his on-premises resolvers. But he says, well, AmazonAWS.com, I trust that that will be an honest namespace anyway, and it would be more effective if you guys just answer that. So I want that answered by the system. And he's got a private hosted zone on the VPC, and he has a private link on the VPC, and that has an internal answer for Kinesis because of the ENI locally, the local IP in the VPC. So he wants that to work. And then he has, curiously subdomained from his private hosted zone, a corporate namespace. I've kind of done that to make this problem harder. And then he has this VPC CIDR, it says 23, and then he has a different IP range in use on premises. So this is not atypical as a setup. So out of the box, we will have a dot rule which says just everything goes to the system. And there are a few more auto-defined rules because there are two private hosted zones. Private link, incidentally, is actually implemented under the hood using a private hosted zone, in case you didn't know that. So that's why that's there. And then there are the two instance names. I'm just dealing with the forward stuff for the minute. So our first requirement was to forward all public DNS resolution via the on-premises resolvers. So we're going to insert an extra rule there, which will, because forward wins over system, that will take over as the default rule. So a query for wikipedia.org will hit the forward rule and go via the on-premises resolvers. Now he said, wants AmazonAWS.com to be answered by Route 53 resolver directly. Whoops. So we create that system rule. And that is more specific than the dot rule, so that will win for that name. So dynamodb.us east 1, this is in a different region, but it matches AmazonAWS.com. So that query will be classified and go the usual path for public queries. Now we had these two effectively private hosted zones. They don't need to do anything here because they got auto-defined rules. They will just work. So for mycloud.com, it will go with the private DNS authority. For kinesis.eus2, which was a private link address, we'll also go to private DNS. Now there was this corp office namespace, corp.mycloud.com, and so we're going to need a rule for that so that it wins over the private DNS rule. But it's relatively simple forward rule, just the same as the dot. So a query for LDAP will go back to the on-premises resolvers. Now, dealing with the reverse, or with the IP ranges, the VPC CIDR, well, we automatically created auto-defined rules. There's one for 10.inadder.arpa because I think it really dates back to good resolver behavior is that a resolver will locally answer RFC 1918 stuff and not ever risk leaking it out to the public routes. But that rule is there. And we've auto-defined specific rules for the /24s. It's important to know about those. Now, there's an on-premises CIDR range. So we create two rules so that the 10.inaddr.arpa doesn't win. And that will allow those records to be forwarded to on-premises. So just summarizing, the key kind of thing, most specific rules wins, just like on a routing table. And that we create rules for private DNS zones, private link endpoints, VPC DNS. But you can override them. And a best practice, typically, if you were to create a dot rule, you don't need, as a general rule, to create an Amazon AWS.com system rule. But if you're creating a dot, we'd recommend doing it. And one thing always when you're doing this is you probably just remember that there are reverse records, and you will want those to resolve in all likelihood. There's a bunch of things like Kerberos and Active Directory which break if they're not set up right. And so the VPC CIDR range, we create those /24s, which means if you want the VPC CIDR range answered by your on-premises, you have to override those /24s. I'll show an example of that in a few minutes. So a very common pattern that's used is with Active Directory. And so there is AWS's managed Microsoft AD, simple AD, and then there's people running their own self-install. And similarly, actually, things like info blocks are used in much the same way. The idea is that you're allocating IPs using an on-premises or self-built system or Microsoft Active Directory, the managed Microsoft Active Directory, and it is allocating these. It's setting names for the host names. It's also answering the reverse names, and it needs to do that, even for the instances inside the VPC. So the standard practice up to last year was very like the forwarding instances pattern earlier. You'd put your Active Directory or your domain controllers either in the VPC or on premises if it was a self-build maybe, and then you would point DHCP at those hosts to answer DNS. And so it looks something like that. Again, it looks very like the forwarding instances. If we're querying that LDAP serve record, it'll just be answered by the managed AD host, though we're crossing AZs again. And this looks very like forwarding instances. If we want to query S3, it's got to go through the managed AD host. So it's now taking all queries for this VPC. So kind of summarizing this, it works very like the forwarding instances. It has some of the downsides of the forwarding instances. Windows, not unlike Linux, tends to focus on the first name server it gets. So you will tend to see a lot of hot spotting on that first instance. And this scaling limit of 1,024 packets per second on the one instance that's taking all the traffic becomes a problem again. I talk occasionally to one of the engineers who works on managed AD, and they see that problem. You've also lost availability zone isolation because you're tending to query that one magic instance. But you can use Route 53 Resolver for this too. And so the steps are relatively simple. You create an outbound endpoint, and you create a resolver rule for the Active Directory domain, and for each of the reverse records, a /24 for each of the reverse records you want us to answer, or reverse ranges you want us to answer. And then you can change DHCP back if you had changed it, or just leave it on the default of Amazon provided DNS. So here's an example, mydomain.com as the Active Directory domain and a 23. So originally this picture looked like this, and it switches to look something like that. So now all of the instances are using the +2 resolver again. We create one rule that says mydomain.com should be forwarded on premises, or to the Active Directory hosts. And now we have to override, because these are EC2 instances, we assume by default that you're going to want us to answer those. So you have to override those system auto-defined rules. So a query for LDAP in the domain will go something like that. And potentially the second one will be cached at the +2, so it won't even leave the box. If you want to make a query for S3 now, though, that's just going to go the straight path out. You're not even going to leave the, you're not going to leave the AZ, and you're not going to you're not going to bother the AD hosts. So this scales a lot better. There's really a lot of queries just not going through the outbound endpoint, not going to managed AD anymore. One further step, it's not uncommon to have an Active Directory in your VPC and then another trusted directory on premises. And typically, if you're doing that, probably try and take, I was talking before about using forwarding sparingly. You probably want to forward to the most direct directory that you can. So in this case, if there's a query for something under the on-premises domain controller there, you can forward it to managed AD. Managed AD will then forward it to the on-premises data center. So you probably don't want to do that. You probably want to do it direct and have one less hop in the path. So the final topic is one that's come up with quite a lot of customers, just to flesh it out. So if you're managing DNS over a lot of VPCs, we have a lot of customers who come to us saying, well, we have one team who manages DNS for everybody else, and then we have loads of developer teams. And because we want them to have separate billing and separate security permissions, we give them all their own AWS account and their own VPCs. And then, because we want it to be a big flat network, they all have to connect to each other. We'll probably connect it together with peering or transit gateway, something like that. And it's kind of a hub and spoke architecture that we drew earlier, actually. But what you need here is a shared coherent DNS view in general. And that can be a little bit challenging to set up. So in the forwarding instance times, the picture looked something like that. And because the DNS forwarders were sitting in the middle, they could kind of mediate that, and you would make sure that they organized this, configure them correctly. Since then, and given the kind of scaling problems and things that came up there, 4 different strategies have emerged using resolver endpoints. It's an interesting thing when you give like a product out, you imagine it will be used in one way, and then a whole load of other creative solutions show up. So what I'm going to do here is just kind of compare them quickly. So the first solution that people went for, which really is a logical step from forwarding instances, is to change DHCP to just point at inbound endpoints instead of the forwarding instances. The second one is to manage the hub DNS, but use forwarding rules to get queries into the central VPC. The third one is a relatively new feature in EC2 called VPC sharing, which is a lot simpler than these, but it's worth looking at if you haven't seen it. And the final one is to actually share everything, put all of the zones in every VPC, or associate all of the zones and all the rules to every VPC, so that each VPC operates more or less alone. So the first solution is just changing DHCP. So we create a bunch of private hosted zones, we put them in the hub VPC, or associate them to the hub VPC. We create an outbound endpoint so that we can make queries to on-premises. And we create some forwarding rules for that. And then we create an inbound endpoint for the instances and change DHCP across the spokes. So this works. Queries go something like that. It's very like the forwarding instance model. So in terms of pros, it is the familiar model. It's kind of the obvious thing to do, but it has a lot of cons. Those instances are all going to hotspot. Where they used to hotspot a forwarding instance, they'll hotspot an inbound ENI instead. It isn't a very fault-tolerant setup because they will all forward to the first ENI, whatever the IP address of the first ENI is. And if there's a failure for some reason in that AZ, or if that ENI fails briefly, it will impact things worse than you'd expect. We no longer have an instance cache because we're not calling the .2 anymore, which is a bit of a downside. And we have all queries for all of those VPCs headed through a 10,000 query per second limit. It's better than the 1,024 queries per second limit, but it's still a problem. And in practice, there are up to 4 inter-AZ hops. I'll show that again. So when you look at that picture, when that instance makes a query, oops, go back one. It will go through an inbound endpoint, potentially in another AZ, to the resolver through an outbound endpoint, potentially in another AZ. So we've crossed AZ twice, and then we have to cross AZ 2 more times on the way back. So this is a really, really complicated pinball machine. So summarizing, this is not a recommended pattern for us. It's not to say we're not your parents. If you make a decision based on your business and your needs that is the right thing to do, that's totally fair, as long as you understand the limits that it has. The second one is to manage the hub DNS in the same way, but forward via endpoints. So I'll show the picture I think works better. So we put the private hosted zones in the hub VPC, outbound endpoints in the hub VPC, inbound endpoints in the hub VPC, and then we kind of wire those together using forwarding rules. So now we can put rules in the spoke VPC that send queries out that outbound endpoint and go back through the inbound endpoint. And we may also have some queries that we want to send to the on-premises resolver, so we have a set of forwarding rules there. So now, a query starting at that instance for an on-premises, or for a private zone, will go round the loop like that. Again, 4 ways through, or 4 paths, 4 different AZ hops potentially. Now, if we're querying, and if we're querying on premises, we'll have a slightly more direct path. So again, this is somewhat easier setup. You're managing DNS only in the hub. And it is a little better in that if you limit what queries go through that forwarding path, you can probably still send a lot of queries direct out through the resolver. So you won't necessarily send all queries through those outbound endpoints. But it isn't as scalable as the third and fourth model that I'm going to show. So again, we have some scaling limits here that are not great. We have a lot of availability zone crossing, so we've lost the isolation that we usually have. So it's not as failure resilient. There are query costs here. They're probably not that high, so I'm not sure that would be the deciding point for anybody, but it's something to keep in mind. So this is kind of a bit of a compromise, but if you think about it carefully and you forward only what you need to, it can be useful. So VPC sharing is a relatively recent new feature in EC2, or in VPC, and I think it's really a useful way to look at this. So typically, everybody needed their own AWS account, which meant everybody needed their own VPC. But that isn't actually true anymore. You can create a hub VPC, you can create a set of subnets, and you can give a subnet to each AWS account and let your teams launch their instances into specific subnets in your VPC. And now, you're not managing multiple VPCs at all anymore. You don't need transit gateway to connect them together, or peering. And you don't need to manage DNS in multiple VPCs because there is only one VPC. If you already have a setup with 150 VPCs, it might be a bit of a bear to try to switch to this model at this point. You could possibly do it for new instances maybe, but if you were starting from scratch, this is definitely a model I would say worth considering. So pros of this, you don't need hundreds of VPCs. You don't need complicated networking. There were some feature gaps. From what I'm told, it is pretty much at parity now. VPC sharing, there was at one point you couldn't launch NLBs into a shared VPC, but that supposedly is fixed now. But it's something to check, to make sure that everything you can do, or you intended to do, you can do in a shared VPC. There's a little bit of reduced autonomy for teams, but actually most of it was implied anyway. I mean, given their own VPCs, they could decide whatever IP address, whatever IP ranges they wanted to use, but they couldn't really. You had to tell them not to. You had to tell them what IP ranges you wanted to use because you were going to hook them together with transit gateway. So I'm not sure how much that's true. So this is really a best practice. It's very, very much supported. It scales really well. And the last model is effectively sharing and associating so that all of the VPCs DNSs work independently. So we'll create outbound endpoints purely for queries to the DNS resolver on premise. We create forwarding rules for those, and we associate them everywhere. Whatever private hosted zones we need, we associate them everywhere. And now pretty much every VPC will have its own view of DNS. or excuse me, the same view of DNS. If a given spoke VPC creates a private link, that will work in that VPC only, which is typically what you want. So a query for a private hosted zone will just take that direct path, and you're not sending queries. You're minimizing the amount of forwarding you're doing. The outbound endpoints, they have limits, and they will only be used for the specific queries that really need that. And most queries will stay in their local AZ as well. To keep this diagram simple, I've not actually drawn all the AZs. So one other question that comes up a lot is how to handle private link endpoints where you have multiple VPCs. So if you're creating them, if each VPC that needs a private link endpoint for Kinesis or whatever the service is creates their own private link, it largely just works in at least model 3 and 4, 2, 3, and 4 actually. But some people have found that the cost of everyone having ENIs, private link ENIs in their VPCs is kind of prohibitive. So they've liked to create a central private link ENI, and then they need to make it resolve everywhere. So private link out of the box, if you tick the button that says, look after the DNS for me, what it will do is create a private hosted zone on your behalf and associate it to the VPC where the ENIs are. The problem with that is you don't have a way to associate that private hosted zone to every other VPC. But it turns out that you can actually create that zone yourself very easily. So don't have private link do it. So in this example, we'll do ssm.eus2. You create a private hosted zone on the hub called ssm.eus2. And you create an alias record at ssm.eus2 at the top of that zone and make it an alias and point it at the VPC endpoint name. And it will resolve exactly as it would have when private link set things up. But now you own the hosted zone, you can associate it to every VPC. This is a little bit brief explanation of this. There's a blog online which James Devine wrote, one of the other solutions architects, and it explains in detail how to do this. But again, the goal of this model is to give you the simplest, most resilient DNS path with the fewest failure modes and the fewest limits. So if you're looking to scale in particular, this is probably the model to look carefully at. So yeah, this is the most resilient and scalable model. Admittedly, VPC sharing is pretty similar in that. Everybody gets to use the VPC +2 endpoint, or all the instances do at least. So you have local caching, you have AZ isolation. We've minimized the amount of forwarding we're doing, which is a good idea. And it's actually very low cost comparatively. The con that does come up with customers and we're looking at is that private hosted zone sharing can be done between accounts, but it is a little bit cumbersome to do at scale. And it's also not available in the console. You have to do it through the CLI or the API right now. There's also a limit on the number of associations you can make on a private hosted zone. Out of the box, it's 100. That's a soft limit that can be raised. So if you need that, talk to support or talk to us. And this is really a best practice, like in terms of building the most scalable model. Again, we don't want to be parental here. If you feel that model number 1 will do you for the first 6 months of your project, that may be the best thing to do. You guys need to decide. What I'm trying to give you here is the best understanding of the compromises between the different ones. So very briefly, just to round up some best practices. And I'm repeating myself here just to give you some takeaways. Again, we would always say you need multiple ENIs in multiple AZs to make sure that you have no reliance on a single AZ with all the endpoints. I would use forwarding as sparingly as you can. EC2 instances have a good resolver that is better than the inbound endpoint for them. And if you can associate the private hosted zones to each VPC rather than attempting to do forwarding, that will scale better, it will be cheaper, it is generally a better option. And in terms of monitoring, you want to set CloudWatch alarms. If you're reliant on the endpoints, you want to have alarms on them. One of your teams is going to set up some kind of weird code, make a deployment, and suddenly the DNS query rate will shoot up and you may hit a limit. You want to get an alarm then. So a few related sessions. There's a chalk talk that a couple of us are giving. If you really want to ask me anything about this, I'll be around afterward, but if you, alternatively tomorrow morning, NET410 is myself and one of the solutions architects, and there's a few other really interesting ones there as well. So thank you very much for your time.